Okay, so we will continue to consider the half-range expansion of a function defined on a finite interval. Okay, so we consider a function f defined on the interval from 0 to L, okay, and this function satisfies the required conditions in theorem 11.1.2, which is just the representation theorem over the interval 0L to L. So this means that this function is piecewise continuous, all right, on this finite cost interval first, and secondly, for each x in this finite cost interval, f has a left-hand derivative and a right-hand derivative, all right, except at the 2 points 0 and L, where at 0 it is required only to have a right-hand derivative, and at the endpoint x equal to L, we will have a left-hand derivative. Okay, so that is the condition, required condition stated in theorem 11.1.2. All right, now we want to represent f, right, f of x, right, as a trigonometric Fourier series by extending f of x, okay, into a periodic function. Okay. Right. So we want to extend f of x because it's defined only on a finite cost interval from 0 to L, but we want to extend it. Want to extend this function to a periodic function which is defined on the whole real line. Okay. And if we do so, by regarding f of x for x in 0 to L as in a period, right, of a periodic function, i.e., so if we do so by regarding the original function as in a period of a periodic function, okay? I.e., if we draw a picture like here, so this is L, right? And this is 2L, 3L, X, and minus L, minus 2L. All right, and suppose that we have something like here. Okay, so right. Okay, so in here, that this is f of x here, and when we extend f of x as the, okay, so suppose that we okay. All right. Okay, so okay. So in this way, you can see then all right. Okay, so then the Fourier series expansion, the trigonal metric Fourier series expansion of f of x, okay, would has A0, A1, B1, A2, B2, etc. and AN, BN as coefficient. And it contains both cosine and sine terms. Okay, so if we do the extension of the f of x, originally is defined. All right, so this periodic function says that all right, say this is f prime of x. Okay, so you in this extension, of course that we, because that this 2 point the function value of original function f at the 2 endpoints may not be equal, right? In this way, we have to sacrifice, okay? We can, for example, in this way, we just pick up the value of f at x equal to 0, okay? And so that in the definition of this periodic function f prime, then at x equal to L, right, the value should equal to the value at x equal to 0. Okay, so now we have here, so the disparity between f prime and f all right, it's only one endpoint. Okay, so they are equal for all x from 0, starting from 0, and to all the point less than L. Okay, so we have the construction of periodic function f prime. Okay, and as we know, because f prime is a periodic function with period L, so of course that the Fourier series expansion of f prime, all right, f prime here, okay, contain the sine and cosine terms, all right, and so, and this coefficients can be computed by f of x, right, because that in one period, right, as the Euler formula shows that that the computation of the coefficients can be done by considering only the function value in one period. Okay, so this is the idea if we do this kind of extension. Okay, but actually, because we consider two special cases in this section, such as the first case is that the periodic function is even. In this case, the trigonometric Fourier series expansion contains only the cosine terms. And the other hand, if the periodic function is an odd function, then its trigonometric Fourier series expansion contains only a sine function terms. Okay, so this is what we will adopt here. So, but we can simplify the trigonometric Fourier series expansion, okay, by using, right, either one, using even periodic extension, we call F1 of F. So maybe I will use FE, all right? Right? Or add periodic extension FO of F, okay? Right, so i.e. The definition of the even periodic extension is here. Is that we define, okay, maybe I write here, the f of Ex, okay, is equal to f of x for x in from L, okay, and if x is in between L and 0, okay, we have f of minus x, okay. All right, so first of all, we have that. Okay, and then we let 2L is equal to f of x. Okay, so the even periodic extension is like this way. So now, and the odd periodic extension becomes 2 here. So this is f of x. Okay. And for 0, x equal to L, and it's 0 when x equal to 0, and then f of minus f of minus x, okay, when okay, let me see. We have okay. So we have okay. Now the endpoint, because minus f of minus x for okay, for the okay left hand side of of 0. All right, so we have that. So let me draw the picture. Okay. Again, we have okay. So our original function. Okay, it's as we know. Okay. This is f of x here. To construct the even periodic extension, we first of all, build so that so both extensions has period 2L. Okay, right. So this is L, this is minus L. Okay, and 2L. This is 3L. X here. And 0 to L minus 3L here. Okay, and so now we do the extension here. Okay, right. So the construction, we want to construct the even periodic extension. Now at this interval from 0 to L. Okay, including the two endpoints, f of e of x is equal to f of x exactly. Now, to be an even function, so that in here, okay, so exactly we have, okay, so let me construct it. So this is f of ex, all right. So now, so we have okay. So now the minus L has the same value as L. Okay, and so we have okay, all right. So as you can see, when x is between minus L to 0, then the value is actually, because when x is between minus 0 and minus L and 0, then minus x is in between 0 and L. Okay, so you can see that when x equal to minus L, all right, so Fe minus L is equal to f of L, right? So the value here, the Fe minus L is equal to FL. Okay, so that we have that. All right, and you can see that for this even periodic extension, the value of this even periodic extension at L and at the mass L's are the same, right? So you can see this, the values of this even periodic function at both endpoints here are the same. Okay, and so we can construct right here, yeah, okay, run period, and okay, so now this has become an even periodic function here. Now the construction of R, the periodic function, okay, is here. Zero L, 2L, 3L, minus L, minus 2L, minus 3L. Okay? All right, and so all right. So now we now construct the periodic extension. All right, and so so for here we have okay. First of all, at the two endpoints, okay, we have up. Okay, so that this is the originally. Okay, so this is f of x, but we want to construct FR out the periodic extension. All right, now. So that the R periodic function is equal to f of x when x is in between 0 and L, but may not include both endpoints. So here we just exclude the both endpoint 0 and L here. The reason is here, because that to be an R, the extension one, the space is not enough. Okay, so maybe okay, yeah, okay, maybe. All right, so okay, so that to be an odd function, okay. So when this is positive, and at here you should have a negative thing. All right. So this go to there. All right. So there's not enough. Maybe I will draw it. Okay. Okay. Maybe so the space is not enough. Okay, so okay, yeah. Minus L, minus 2L, and minus 3L, and this is 0. Okay. All right. So originally we have that one. Okay. So this is our f of x. Okay. F of x here. And to construct the periodic extension. So first of all, for all x in between 0 and L, not including 0 and L, right? So So this is not a solid circle, all right? And so in here, that to be an odd function, okay. Now, all right. So so we have right. So we have okay. We have that. Okay. So in here that the point. So you can see that if this is x, all right, and this is minus x, okay, and so you can see f of e minus x, right? So for all x in between 0 and L, fe of minus x, all right, and fe minus x is here, right, and so minus x will in between minus L and we have okay, minus x is in between 0, and then f r of x by definition, okay, by definition here, right? Because now minus x is in between minus L and 0, so we have minus f of minus x, okay, and this is minus f of x, okay, this is minus x of x, all right, and this is minus f of sub o x, okay, because by definition, when x is in this range, then f sub o x is equal to f of x. All right, so we have, all right, so you can see that, sorry, minus x, all right, minus x, so you have, so the argument minus x is in between minus L and 0, and by the definition here, okay, we have here, all right, and so this is minus of f of x, but when x is in between 0 and L, then by definition f of x is equal to f sub 0, f sub o of x, and so you can see that this show you the odd functions here. Okay, so this is the way, and so the extension, as you can see, this is becomes 2. Okay, here, there. Okay, and here. All right. Okay, and okay. All right. So the green figure illustrate the other periodic extension of f of x here. Okay. Now, so to be so you can see to become to an odd function. Now we didn't define, right? We haven't defined the value of this odd periodic extension at x equal to 0. But to be as we know, because fr minus x is equal to f of function, as to be an odd function, right? For all x in R. So this implies that f odd minus 0 is equal to f of f odd 0 here. But f minus 0 is f of 0. So this is implies as f odd 0 should be equal to 0. Right? So this is the must. How about also also this implies f of minus L, as we know that this is equal to f of L. Okay, so you can see as an arc function, so you substitute x equal to L, you get this one. But as we know, as a periodic function, this function value is equal to f0L, okay? Because as a periodic function. So you can see f(O) of L is equal to minus f(O)L. So this also implies f(O)L is equal to, again, is equal to 0 and f(O) minus L. Okay. So you can see that for R, the periodic extension, that you should know that you should assign 0 here for x is equal to 0 and plus minus L. Okay? Plus minus L here. And then you extend, define x plus 2L to be f of x. Okay? For all x in R. Right, for all x in R. Okay? Right. So that so you can see for even periodic extensions, right, you can preserve the original function 100%, okay, including the two endpoints, right? So you see that they are equal, right, for x in between 0 and 1, including both ends. But for all the periodic extensions, all right, you are guaranteed that this function value is equal to f of x when x is in between 0 and 1, but may not include both either endpoints. All right, and they will be the same if and only if that f of x is 0 at x equals 0 and at x equal to L. Okay, because this is the requirement here. All right, so now we have to assign here. All right, so 0, 0, 0, and 0. Okay, and 0 here. So this is the periodic extensions. Okay. All right, and so now, okay, so now f e of x and f o x are periodic function with a period 2L and satisfy the required conditions, right, in theorem 11.1.2. Okay, so that both of them are piecewise continuous over mass L to L. So both of them are piecewise continuous on this finite cross interval. And both of them has a left-hand derivative and a right-hand derivative at every point x in R. Okay, so that they satisfy them, and so that we can apply the representation theorem to both of them. Okay, both of them. So now, in particular, so now. And then by theorem 11.1.2, the trigonometric Fourier series generated by FE and FOX. All right, so that A0 plus summation you will want to infinity an cosine n pi divided by Lx and summation n equal to 1 to infinity bn sine n pi Lx. Okay, so this is the all right, maybe I will write it this way. The trigonometric Fourier series, I have to say A0 plus summation from to infinity an cosine n pi divided by L of x and summation n from 1 to infinity and bn sine n pi divided by L of x generated by Fe of x and Fo of x respectively, with here we know that A0 is 1 over 2L and F of x, right? Because this is the trigonometric Fourier series expansions of the even periodic function, and so we know that we can only have the constant term as well as the cosine term, and so the constant term coefficients is here, all right, and because f of e is an even function, all right, so this is 2 to L and 0 to L, f of e, f of x, okay. So this is 1 over L here, and 0 to L, but as we know, in this range, that we have f of x, okay, so this is f of x, and the dx, okay. Okay, and an is 1 over L mass L, f e x, and cosine n pi divided by L x dx here. And once and again, this is 2 and L mass L. Okay. Now because this is an even function and cosine is also even, so the product is an even function again. All right, and so this is, you can just integrate, okay, half of the period. All right, so this V1 and Fe of x and cosine pi Lx dx. All right, and when x is in between 0 and L, we can replace f sub ex by f of x by original fx. Okay, so now an can be computed by the integral of from 0 to L of this integrand, and Bn here 1 over L minus L to L, and Fr the function, and the sine pi Lx and dx. Now, because this is R function and sine is also odd, so the product is an even function. Okay, and so this is 2 divided by L from 0 to L, and f of x and sine pi by L and dx. All right, and in this interval, right, when x from 0 to L, the fo function is equal to f of x, so we can replace, okay, this one, 0 to L, f of x, and the sine pi Lx and dx. Okay, all right, so you can see that either one has coefficients, and this coefficient actually can be computed, all right, by evaluation of an integrand over half period from 0 to L. You can see from 0 to L, all right, from 0 to L again. Okay. All right, so now, so both of them, okay, so this one and this one, they are trigonometric Fourier series generated by even a periodic extension and odd periodic extension. All right, and so we have, and from the representation theorem, we know that f of e of x, all right, equal to sorry, so that a0 plus summation from 1 to 0 and bn an, sorry, an cosine n pi divided by L x, which is equal to f of ex. Okay, and if for all, okay, so for all x in R, where f of e is continuous, okay, and is equal to f e x plus minus L f e x plus, right, for all x in R, where f e is discontinuous. Okay, so this is what we have. All right, and in particular, right, is equal to f of x for all x in 0L. Okay, where f x continuous. Okay, so that f is continuous. And as you can see that, for even periodic extension, you can see that the function, the FE function, must be continuous at well, not necessarily. I mean, okay, I'm sorry. I have to say that if f is continuous, all right? But at the okay, and is equal to f of x minus plus f of x plus divided by 2 for all x in 0L, where f is discontinuous. Okay. Good. Okay. Okay, and for this trigonometric series expansion, because sine and summation, and from 1 to infinity, Bn sine n pi divided by L x is equal to f of 0 x, right? For all x in R, where Fe is continuous. F sub O is continuous. Okay, and it's equal to Fox minus plus Fox plus divided by 2 for all x in R, where f x discontinuous. Okay, now it's equal to f of x for all x in 0 to L. Okay, because that f of x is equal to f of x when x is between 0 and L, but may not include 0 and L. Okay, so just here where f is continuous. Okay, where f is continuous. Okay, and we have that, and f of x minus plus f of x plus divided by 2 for all x in 0L, where f is discontinuous. Okay, right. So we can specify. You can see we can specify basically that this trigonometric Fourier series containing only a sine term is equal to the original function values for all x in this open interval at every point in this open interval, such that at that point f is continuous. But when f is not continuous for a point x in this open interval, then this trigonometric Fourier series will converge to the average of the left-hand limits and the right-hand limits. Okay, and for we don't for the when x is equal to 0 or equal to L, right? As we know that this function, okay, this function, you can see this function. This has 0 value at x equal to 0 and L, right? You can see that it is 0, and then of course this is 0, and if x is L, this m pi is also 0. All right, so this one always the value of this so that the sum of this trigonometric Fourier series is 0 when x equals to 0 or L. Okay. Okay, so you can see this is 0, all right? This is 0 for when x is equal to 0 and L. Okay, and so it depends on if f of 0 is 0, then of course this you recover the value. But if f of 0 is not equal to 0, then you can't recover the value of f at x equal to 0 by this trigonometric Fourier series. This is the same when x equal to L, okay? So that we can have this result, okay? All right, so if you want if we want Fourier series expansion of the original function by using the cosine functions, then you should use the even periodic extension. But if you like the trigonometric Fourier series expansion contains only the sine function terms, then you better to use the periodic extension, okay, like this one. But you may not be able to represent the function f at x equal to 0 or at x equal to L. Why? Because that the sum of this series is always equal to 0 when x equals to 0 or L. Okay, so that is what we learned from them. All right, and so that we call both of them. So this one and this one, we call them as so this is called, all right, so from this result, so we know that this one is called even half range expansion. Right, of f of x, of f, okay, and this one is called odd half range expansion of f, okay. All right, so this is really depends on your requirement, either to use the even half range expansion or to use the odd half range expansion. Okay. Okay. So now we will proceed to the third section. We will talk about forced oscillation. All right, and except this is section to illustrate application of the theory of Fourier series expansion to solve differential equations. Right? So let's say to apply the theory, right, of Fourier series to the solutions of differential equations, including ordinary differential equations. Okay, we need to make sure that the validity of the interchange of the limiting process, because that because we are talking about series, and series is just it's just an infinite sum of functions. All right. So to take the sum of the theories, they involving the limiting process, and but in dealing with differential equations, we have the differentiation process. All right. So we have differentiation operations. Okay, as we will see from an example. Okay, so we should deal with the validity of the interchange of the new process and the differentiation operations. All right, and so this involves the concept of uniform convergence. Okay, of a sequence of functions. Okay, all right. So so now we define what is the uniform different convergence. Right. Now a sequence f sub n of functions, right, defined on an interval I. So the interval I may be finite or infinite, right, of the real line. Okay, right. So a sequence of function, right, is said to converge uniformly on I, right, so converge uniformly on the interval I to a function f defined on I if for any epsilon greater than 0 there exists a positive integer capital N such that you evaluate the difference, the distance. All right. So you want the distance, right, of f of n, and the f is less than the epsilon. Okay. Then we can find an integer, so that if the index little n is greater than or equal to n, so if n little n is big enough, then the difference, the difference of the function value would be less than epsilon, and this is for all x in I. Okay, so it's uniform because that we approach that. So the function, the function fn will approach to f, to the limit function f. Okay, approach them in over the whole defining range. Okay, defining interval I. Right. So let me illustrate the uniform convergence by a figure. Okay, so it's what we have here. Right? Suppose that the interval is from, right? So the interval, say, from A to B. Okay, and the limiting function. Suppose that we have like. All right, so this is the limiting function f of x. And we say that the sequence of function converge to this limiting function f of x uniformly on I. Okay, then so if we specify an adder epsilon, okay? So if we specify an adder called epsilon, okay, so the adder epsilon, all right, so this say here, so that would be okay, so this function, this one is f of x plus epsilon, and all right, so this one is f of x minus epsilon. Okay, now so we have two bounding curve, all right? So and for all, so we have a capital N, right? Such that for every f sub n, when little n greater than or equal to capital N, a typical function could be like that. Oh. So that you may have, okay, right, so that this is f of nx, right, for all n greater than or equal to n. Okay. So that the figure of f sub n of x for any little n greater than capital N, that the figure can only okay. Can only be okay. You can't have two values. Okay. So you can have, okay, like that. Okay. If you have another function f sub m, suppose you have another function f sub m, then you can have, okay, all right, and so okay, so you have that. So that's the meaning of uniform convergence. Okay, and when epsilon becomes smaller and smaller, right? All right. So this tube become narrow and narrow, then the capital N may be bigger and bigger, all right? So that when little n greater than or equal to capital N, that the figure of the function still in the narrow tube, within the narrow tube. Okay. All right. So this is the definition of uniform convergence. All right, so it is clear that if this sequence of function converges, okay, uniformly on I to a function f on I, okay? Then, if we consider function value at any given x on the I, then this is become to a sequence of numbers. Okay, a sequence of numbers will converges to the function value f of x for each x in I. Okay. All right. So that is, so I will say uniform convergence implies pointwise convergence. Okay, but the converse may not be true, right? Of course. All right, so now we will state a theorem which will be useful in this section. Theorem 11.3.a. Okay, so let f of fn be a sequence, okay, of differentiable function okay on a finite cross interval AB here, right? So suppose we have that. If when we consider some specific, so if there existed a point x sub 0 in this finite cross interval, right? And this is sequence of numbers, all right? This sequence of numbers converges, okay, for some x0 in AB interval, right? The first condition. And the second condition is that the derivative, right? The derivative of this sequence of differentiable function converges, right, uniformly on AB. Okay, right? So if we have both conditions, then we have two results. The fn function, right, will converge, right, uniformly on AB to a function f. Okay, so this, and this limiting function f, right, is differentiable. Okay, it's differentiable on AB, and its derivative, okay, its derivative is equal to the limiting, right? Because we say that this is the sequence of derivative of fn, right? So, and it converges uniformly. Okay, of course it converges pointwisely, but we have a stronger condition. All right, so this limit will exist. Okay, for all x in AB. And this shows that, this actually shows that the derivative, you see, the f of x is the limiting function. Okay, and then you take the derivative. All right, this is equal to, you exchange the sorry, this is the okay. So we get a right. Okay, so the yellow box actually can be written as the green box you see here, because before you take the derivative, the f of x is the limiting function, okay, of this sequence of functions, right? Right, and the second result says that this limiting function, okay, is differentiable. Okay, differentiable here, and the derivative is equal to the limit of the derivative of f sub n. So you can see you can exchange the differentiation operation with the limiting process, right? You can exchange the order of them. Okay, so this theorem tell us that that the exchange of the limiting process and the differentiation operation can be guaranteed by these two conditions here. Okay, so that you have to check that for a sequence of differentiable functions, you have to check that the sequence of their derivatives, all right, converges uniformly on AB. Okay, to certain function. Of course, I didn't right here. All right, but just we know that it's converged uniformly on AB. And we also should know that this sequence converge at some point. All right, so we know that there is a point x0 in this finite cost interval AB, and so AB interval, and so that this numerical sequence converges. Okay, all right, and to guarantee these two results. Right. Okay, and I give a reference. Okay, in my lecture notes to find a proof of this theorem. Okay, so I will not give a proof here. All right, and we can restate this theorem, all right, in terms of series, because to take the series sum actually is to take the limit of the partial sum function. Okay, so now by reformulating the previous theorem, in terms of series, okay, we have the following theorem. So we call it a theorem 11.3.b. Okay, so we let f sub n be a sequence. Okay, be a sequence of differentiable function on AB. Okay, if first one, if the series, okay, summation m from 1 to infinity, fn of x0 converges, all right, for some x0 in the finite cost interval AB, and the second the series of the derivative, right, of the derivative converges uniformly. Okay, converges uniformly on AB. Right? So then 1, the series right, of Fn itself, right? So the series of functions, of real functions, well, converges, okay, uniformly on AB to a function, f, and secondly, f is differentiable. Okay, f is differentiable on AB, and its derivative f prime of x is equal to the sum, the series sum, all right, of the derivative of f sub n, okay, for all x in AB. Okay. Okay. So to apply, so that this is the reformulating, a reformulation of the previous theorem, because that if f sub n be a sequence of differential functions, then the corresponding statement is here. We let x n of x to be, okay, from 1 to infinity to n of f sub k of x, right, for all n 1, 2, 3, etc. So that be partial sum functions of the series, okay? All right, so this is the partial sum function of the series. All right, and so that says that when Fn be a sequence of differentiable functions, because each f sub k is differentiable, so the partial sum is also differentiable. Okay, so now this implies that the partial sum function is a sequence of differentiable function on AB. And the series converge, which says that the numerical sequence of the partial sum function value, right, at x0 converges, right? So this converges, and the series sum, okay, converge uniformly means that the xn prime, okay, xn prime. So the partial sum, the sequence of partial function converge uniformly on that. Okay. Then the xn converge uniformly to a function f, right? And f is differentiable, and okay, and this becomes to the limit for n goes to infinity, and xn of x. Okay. For here. Okay. So you can see that you just apply this theorem to the sequence of partial sum functions, okay, and to get this result. All right. Now, so we have to test. We have to test the uniform convergence, right, of a sequence, right, of functions. And the next theorem provides a simple test. All right, we call it theorem 11.3.c, and people usually call it a Weierstrass. Okay, so Weierstrass test of union convergence. So we let f sub n be a sequence of functions, right, defined on an interval I, okay, such that we know that for each f sub n has an upper bound, right, for all x in I. All right, so for each sub n, we have upper bound m sub n. Okay. So now, if the series, okay, the series n from 1 to infinity of this upper bound converges, okay, right, then the series okay, of f sub n, okay, converges uniformly on I. Okay, so this is a very good test to answer the question. So if you want to know whether this series sum of the derivative converges uniformly on AB, then if you are able to find upper bound for the derivative of f sub n, all right, for all x in the interval, and then you know the series sum of f sub m sub n converges. So if this numerical series converges, then this, right, this series sum of function of the derivatives converge uniformly on the interval. Okay, so that is a very good test, a very simple and a very good test. All right, and the proof, I provide a proof. Please see the lecture notes. Okay, we'll see the lecture notes. So I omit the discussion of the proof here. Okay. Okay, so now we now have a tool. Okay, so we now to illustrate how to use the previous theorems to apply the Fourier series expansion to the solution of ordinary differential equations. Okay, so let's consider so that the current. So we consider an RLC circuit. All right. So the current I of t of a serial an RLC circuit. All right. With a voltage input U of t is governed. So we have the So you can see R, L, and the capacitor C circuit. All right, and we have E of t, and the current is here. Okay, so we have RLC here. So this is a typical circuit. Okay, we got circuit here, and so the driving force is a voltage input, and we have current up to here, and we know that in circuit theory that the relationship between the voltage input and the current in the RLC circuit, in the serial RLC circuit, is governed by a second order ordinary differential equation. Okay, so let me, okay, here, I write here, is the inductance of the inductor, L, and the I double prime of T, right? So this is the second derivative of the current plus R times the first derivative of the current plus 1 over C of the current is equal to the derivative of the voltage signal. Okay, so this is the ODE, the ordinary differential equations, and it's clearly this is a second order ODE we have with constant coefficient, and of course it's linear, right? You can see this is a linear ODE. Okay. Okay, so we know that R, where R is the resistance of the resistor, L is the inductance of the inductor, and the C is the capacitance of the capacitor, right? Right, as we know, we learn from ordinary differential equation, we know the general solution. The general solution of the ODE, okay, is the sum of a homogeneous solution, right, and a particular solution. Okay. All right, and as we know that the homogeneous solution actually has two degree of freedoms. All right. So that and since the ratio R divided by L is positive, of course, because that R, L, C are all positive numbers. Okay. This ODE, right, govern, all right, damped, all right, system, so that any homogeneous solution, so any homogeneous solution, say Y sub HT, okay, becomes 2. Let's see here. Divided by 2LT. So we have it's damped. So that you can see that we have this negative exponential term, and C1 plus exponential square root of R square minus 4L divided by C, okay, and divided by 2L and T. Okay, so this C1, C1 times this exponential term, plus C2 times another exponential term, minus the square root of R square minus 4L divided by C and divided by 2L T. Okay, and this is when the R square minus 4L divided by C is positive. Okay, in this case, but if R square minus 4L divided by C is 0, when we have 0, right? When we have 0 terms, then this is become 2. This is a degenerate case, so we have C1 plus C2T. Okay, and if R square minus 4L divided by C is negative, okay, when this is negative, then this is the damping term, and here we have cosine term, cosine oscillation. So this is the cosine term 1 over LC minus R square divided by 4L square and T, right? Plus C2 sine square root of 1 over LC minus R square divided by 4L square and T. Okay, so this is as we know, there are 2 degrees of freedoms here, C1 and C2. Okay, so that we have homogeneous solutions here, homogeneous solutions, and as you can see, for any case that we have, so that any homogeneous solution will vanish. Okay, as t goes to infinity. So basically, because of the resistance, right? So that the homogeneous solution will go to vanished, right? When with IE without. So without so that this homogeneous solution means that when the voltage signal is 0, okay? When this is 0, you get the homogeneous solution. So without the external force, all right? So without external force, E prime of t, the current, of course, of the serial IOC, okay, circuit. Okay, will diminish to 0. Okay, will diminish to 0. Okay, and is 0 exponentially, exponentially fast to 0, exponentially fast. Okay, so without the voltage driving forces, because of the resistance exists here, so this is a damped system, and so the homogeneous solution means the current will diminished exponentially fast. Okay, this is wrong. We know that. So in steady state, means that as t goes to infinity, so we will see so that that's as t goes to infinity, the solution, all right, so the solution of the ODE approaches the steady state solution, steady state solution. Okay, so which should be a particular solution of the ODE, right? So this must be a particular solution. All right. Now in circuit theory, we usually do some so-called Fourier analysis, right, by applying a special kind of signal. So if the voltage, right, input E of t is a sinusoidal wave. Okay, so if the sinusoidal wave, then E prime of t is also, all right, a sinusoidal wave, right? Right, says that. So we says that E prime of t as a sinusoidal wave is A cosine omega t plus B sine omega t. Right. So omega is just the angular frequency, all right, of the sinusoidal signal. Okay, so that E prime becomes 2. This one. Okay, so this is the so-called the steady state analysis, right? So that, and so by the method of undetermined coefficient, so by the method of undetermined coefficient, as you have learned from ODE course, coefficients, the steady state, all right, so the steady state solution, of t, okay, of this ODE must, okay, must also be a sinusoidal wave with the same frequency. Omega, i.e. the steady state current becomes to A star omega, and the cosine omega t plus B star omega, and sine omega t. Okay? So you can see that the response depends on the angular frequency. Okay? Even though the amplitude, the A and B here, the amplitude here keeps constant, but when we change the angular frequency, the response here will change when the angular frequency is changed. Okay. All right. So this is we have known from the study of ordinary differential equations. Okay, so we have to say where both A star omega and B star omega, the response depend, okay, on the angular frequency omega. Okay, so that we know this from the study of ODE. Now, if the voltage, so if the voltage input E of t, right, is continuously differentiable, okay, it's a continuously differentiable periodic function wave, okay, with a period, all right, 2 pi, okay. Then E prime of t, okay, is continuous periodic wave, okay, with a period, okay, 2 pi. Okay, and we further assume that E prime t, okay, has a left-hand derivative and a right-hand derivative at each t in R. Okay. right? So this is very common. The voltage is a periodic wave. For example, some clock signal. Okay, so that and we assume that that the voltage signal is continuous differentiable. So its derivative is a continuous function, right? So this is a continuous function and also a periodic function. All right, and so with a period 2 pi. And this implies that E prime of t is piecewise continuous because it's already continuous. Right? So it must be piecewise continuous over one period of time. And we also assume that E prime of t has left-hand derivative and a right-hand derivative, right, HT in R. So in that way, so now by theorem, given 0.1, 0.2, okay, the trigonometric Fourier series okay, generated by E prime of t, where converges, right, to E prime of t for all t in R. Right, so i.e., we know that E of prime of t is equal to the limit as m goes to infinity of a0 plus summation n equal 1 to e to m and the an and the cosine nt plus bn and sine nt, right? Where we know a0 is 1 over 2 pi E prime of t and dt, and an is 1 over pi and E prime of t cosine nt dt, and bn is 1 over pi and in the E prime of t sine nt and dt over n greater than or equal to 1. Okay, so we know En prime is the limit of the partial sum function, right? So the trigonometric Fourier series generated by E prime will converge to the E prime of t for all t, because that E prime of t is a continuous function, right? So by the representation theorem, we know that this is true. So this is for all t in R. Okay. Okay. So now we will, so suppose, so now here we suppose that the input, right, voltage, okay, is a component En of t of Et with E0 prime of t is equal to A0 and En prime of t is equal to An cosine nt plus Bn sine nt, for all n greater than or equal to 1. All right, so suppose the input voltage is a component, En of E, right? And with the with the derivative of the zeroth component is A0, and the derivative of the nth component, ENT, is this sinusoidal wave here. Okay, suppose that. Okay. Then so by our discussion here, all right. So if E prime t is a sinusoidal signal here, then the steady state solution of the current is also, you can see, it's a sinusoidal wave again. So now the corresponding steady state solution, we say I sub n of t should be, right? So when E prime is a constant, as you can see, if this is a constant, and a particular solution, right, is also a constant, right? Because when IT is a constant, then derivative, first derivative and second derivative are all zeros. Okay, so you can equate them. All right, so that we know that I0 of t is also a constant, because this corresponding to zero angular frequency. All right, and the nth component, if we have ENT, then the steady state solution INT would be AN star cosine NT plus BN star, okay, sine NT, right, here. Right? So of course this one depends on AN as well as the angular frequency here and here, okay? Right, so that only one single index will be enough. Okay, and this is for n greater than or equal to 1. All right, so that's by the linearity, okay, of the ODE. Okay, in above. All right, so the ODE is here. This is a linear ODE. All right, so by it is reasonable, okay, to conjecture that the steady state, so the steady state solution I of t of the 4 periodic voltage E of t, x here is IT to be the summation, okay, and t here, which is equal to A0 star plus summation n from 1 to infinity an star cosine nt plus bn star sine nt. Okay. The reason why we call it a conjecture, because that if we include only finite number of the components, say for n from 0 to some m, then of course this is true solution. Okay. So if you include finite number of components, then this is indeed a solution, a steady-state solution. But if you include infinitely many terms, right, then this is questionable. Okay, so we just say this is a conjecture, so that the solution is just a series sum. Okay. All right, so we need to justify. So we need to justify the conjecture. We have to, okay, to justify conjecture. So we have to check something, right? First of all, to check if the strong hypothesis, okay, in theorem 11.3.b holds. Okay, so we want to know that whether, right, that converges. Okay, so we want to check if the strong hypothesis in that theorem holds. So that the interchange, right, of the limiting process, here we say the series sum process, and the differentiation operation, right, is valid. So that is, we have to show, right, so we have to show that the series, first of all, we have to show that the series of sum converges. Right, so we show that this converges for all t in R, and okay, and that. And that I prime t is equal to summation of in prime of t, and I double prime of t is equal to summation of t, right? Right, so we have to show that the series converge, right? Right, converge and equal to IT, right? And the derivative you can have, so that you can exchange the order of the limiting process and the derivative to make sure that once you do the substitution, okay, then this becomes true. Because that we know that the second derivative is equal to this series sum. The first derivative of I of t is equal to this sum, and it is just the series sum here. Okay, it converges. Okay, because we have shown that this is true, so that this is come to L in prime t plus R in I1 double prime t and t plus 1 over c in t. Okay, and for each one, right? For each, so this is just the ODE here when the input is the nth component, so that this is equal to the En prime t. Okay, En prime t. But as we know that okay, that the En prime t is equal to E prime t. Okay, here. Okay, because that we know this is true, so the series sum is equal to En prime t. Okay, and this is the as we know that this is called okay, so this is the as we know in here, so this is the okay, this is E0 prime t, okay, and this one is equal to the En prime t, okay, so that the derivative of the nth component, and this is derivative of the zeroth component together. All right, so the series sum of E0 prime t, En prime t is equal to E prime t for that. Okay. All right, so we can make sure. So what we have to do, and so at that, in this case, then we actually prove that the I of it is indeed a steady state solution corresponding to the periodic signal E of t. Okay, so what we need to do is to show that this series sum converges. Okay, and we want to show that the limiting process and the differentiation operation, okay, can be exchanged. So this is the case. We can exchange them. So that means that this is just saying that d dt of series sum is equal to okay, right, and here is that dt again, the series sum prime of t is equal to okay, because once we down this one, and we have to show that we can further take the derivative of the derivative. Okay? So that's the sum here. This is that, and equal to that. So again, this is the further exchange of the limiting process and the differentiation operation. Okay. Okay. So that is this is the strategy that we need to do, so this is to check that this is indeed the IFT. Okay, this IFT, as we conjectured, this one is indeed the steady-state solution of the periodic, the full periodic voltage EFT. Okay. Okay. So let's take an example to illustrate this strategy here. So we take the example. Okay, so we consider an ODE, okay, which governs a damped system under a periodic driving force. Okay, so we have Y double prime plus 0.05 Y prime plus 25 Y equal to the driving force R of T. And here the R of T, okay, the driving force is T plus pi over 2 minus T plus pi over 2. If minus pi, T between minus pi and 0, and between 0 and pi. And the driving force has period 2 pi. Okay, so let me draw the picture here. So now minus pi, this is pi, and this is T. All right, and so for here, we raise to pi. So when T is minus pi here, okay, we have minus pi over 2. Okay, so okay, and so the range. So we have this one. This is minus pi over 2, and here is pi over 2 here. Okay. All right, and this is R of T. And so we have minus, so we go over to here. Okay, so this is a triangular wave. This is 2 pi and 3 pi. So we have the 1 go down, and minus 2 pi, minus 3 pi. So we have go down here. All right, so we have triangular wave R of T. So the driving force is a triangular wave, and as required that the driving force is a continuous function. So you can see this is continuous function. Okay. All right. So R of T is a continuous periodic function with period 2 pi. And as you can see that it has left-hand derivative and right-hand derivative at every point. Okay, and in here you can see that except the integral multiple of pi, okay, if that if x is not integral multiple of pi, that is differentiable. Okay, so that the left-hand derivative and right-hand derivative are equal. Okay, for example, in here the derivative is you can see this. I think this is 2. Okay. Yeah, this is 2. 1. I'm sorry, 1. And in here the derivative is -1. Okay, but at the integral multiple of pi, for example, at 0, the left-hand derivative is not equal to the right-hand derivative. So at 0, the left-hand derivative is equal to 1, but the right-hand derivative is equal to -1. So they are different. So that at this point it is not differentiable, of course, but it has a left-hand derivative and right-hand derivative. Okay, so R of t satisfy the condition in our representation theorem. Okay, all right. So so now, we can see that. So now note that R of t is a continuous periodic wave, all right, with a period 2 pi, and has R of t and has left-hand derivative and right-hand derivative at each t in R. Okay, so that it satisfy the conditions in the representation theorem. All right, and so that the trigonometric Fourier series generated by the driving force of t can be computed. All right, and so that R of t is equal to, and you can see that the R of t, the driving force, is an even function. Okay, it's an even function. So so it consists of the cosine terms. 2k plus 1 square cosine 2k minus 1 and t for all t in R. All right, so we have an exact representation, and the constant term is 0. All right, for this case. All right, so we have that. So R of t. So this is exactly for every t in R. This triangular wave is equal to the series sum, right, of cosine functions. Okay, so this result is from our representation theorem. Now for n equal to, because this the frequency except you can say is odd, all right, etc. We let yn be the steady state solution, okay, of the ODE, okay, with the input, okay, 4 divided by n squared pi, right? 4, right? Divided by n squared, okay, pi and cosine nt. Right? So that if we apply the nth component of RT, right? N, right? 1, 2, 1, 3, 5, etc. And then the steady state solution is y sub n. Okay, so this is y sub n here, corresponding to the y's component, the nth component. Then we have, right? So it's easy because that this is a cosine signal, so that it's quite easy to solve the second order differential equation. So we have yn t is equal to, if you do the solution, 25 minus n squared divided by the dn, a constant, depend on n, t 0.05 n, and the dn, and sine nt. So as we know, that the response should be also a sinusoidal signal with the same frequency as we discussed before. All right, here, as we discussed before. And so that this is, we can combine them together. We can write them in this way, square root of dn and cosine nt minus theta. And so this is the phase. And where d sub n is the 25 minus n square, take the square, plus 0.05 n square. And cosine theta n, so the phase, the cosine theta n is equal to 25 minus n square divided by square root of dn, and sine theta n is 0.05 n divided by square root of dn. Okay, so these two determine a unique theta n. Okay, in one cycle. All right, so that's the conjecture. So the conjecture steady state. The conjecture state solution is here. It's yt equal to summation k from 1 to infinity y sub 2k minus 1t, and which would be summation of k from 1 to infinity 4 divided by 2k minus 1 square pi. Okay, and 25 minus 2k minus 1 square divided by big D, 2k minus 1, cosine 2k minus 1 t, plus 0.05, 2k minus 1 divided by big D, 2k minus 1, and sine 2k minus 1 t. Okay, so that we have to, this is the conjecture steady state solution. And we haven't yet shown that this series converge, okay? We haven't shown that. So we have to show that this converges. And the sum of this series will be, say, that yt. So this is our steady state, the conjecture steady state solutions. Okay, so this is conjecture solutions. So to justify, so we have to justify, right, as our strategy. So to justify, okay, this solution, right? So we consider, right? We consider the derivative of the answer solutions, right? And also the second derivative of the solutions. Okay, so to judge the solutions, we consider Yn prime of t. So when we take the first derivative as well as the second derivative, we know that this is m pi and minus 25 minus n squared divided by dn sine nt, okay, plus 0.05 n divided by dn and cosine nt. Okay, and this one is minus 4 divided by m pi square root of dn, all right, and the sine nt minus theta n, and theta n has been computed before, and the second derivative of Ynt becomes 4 divided by pi here, and minus 25 minus n squared divided by dn cosine nt minus 0.05 n dn sine nt here. Okay, so this is minus 4 and pi square root of dn and cosine nt minus theta n here. Okay, now we need actually we need uniform convergence of serial sum. So we will use the Weierstrass test. Okay, now to apply Weierstrass tests, now we will estimate, we will find upper bound. So it can be seen that first of all, the Yn of t, right? So now with Yn of t, the absolute value of Yn of t here has an upper bound. And look at here, because the cosine function is bounded by 1, right? So that we have 4 n squared pi and square root of dn here, right? So this is about Yn, and the derivative of Yn has also upper bound here. Again, from here we know the upper bound is 4 divided by m pi square root of dn. And finally, the double derivative, okay, is upper bounded by pi square root of dn here. Okay, so for all t in R, right? So we have upper bound. Now since we look at dn, recall that dn here, dn is the sum of these two squares. Okay, and so we will use the first one, all right, the first term, the first square. So we know this is equal to 25 square, right? So dn is greater than equal to the first term. Okay, and for all n greater than equal to 1, so that, and then we know n squared minus 25 is greater than equal to n minus 1 squared. Okay, for all n greater than equal to 13. Okay, so if n big enough, we have this inequality. So we have here, right? So when we replace this by this one, so we know that the square root of dn has a lower bound, which is the square of n minus 1 for all n greater than equal to 13. So which implies that? So which implies that if we sum over the upper bound for k from 1 to infinity and 4, okay, 4 and so that here, so this one, so we'll get that. This is pi square root of d 2k minus 1 here. Now we can have that k from 1 to 6, okay, and 4 pi square root of d 2k minus 1 here, right, plus summation for k from 7 to infinity. When k is 7, n is 13, right? N is 13. Because n is equal to 2k minus 1, right? And so this one, this is become 2 pi, but square root of dn when n greater than or equals 13 has a low bound. All right, so when we put into the denominator, we get the upper bound. So here we get the 2k, all right, minus 2 square. And as we know, this is a constant, of course. It's because we have a finite number of terms. But here, because we have k square, so this is serial sum converge. So we know this converge here. Okay, so the upper bound of the second derivative of yn, right? This upper bound when summed together, we find that it converge. Okay, and also since we know that compared with these three upper bound, we know for n square pi square root of dn is lower bounded by 4 divided by n pi square root of dn less than or equal to 4 divided by pi square root of dn for n greater than or equal to 1. So we have, furthermore, we have that the summation of this upper bound for k from 1 to infinity and 4 and 2k minus 1 square pi square root of d 2k minus 1. This sum is finite, and summation k from 1 to infinity and 4, that's 2k minus 1 pi square root of d 2k minus 1 is also finite. Okay, so we have this is finite, and so by the Weierstrass test, let me correct. So now, okay. So now by Weierstrass test, okay, the three trigonometric series, all right, summation k from 1 to infinity y to k minus 1, summation k from 1 to infinity y prime to k minus 1, and summation k from 1 to infinity y double prime to k prime 1. These three will converge uniformly on the whole real line. Okay, so they converges the whole real line. All right, so this validate the Fourier series expansion okay, because it's converged. So we know that this converge, and the limiting the sum is defined to be yt. Okay, so this validates the Fourier expansion of yt, i.e., yt is indeed the sum of k from 1 to infinity y to k minus 1t. Okay? All right, and by theorem 11.3.b, okay, the first and the second derivative of yt have the Fourier series expansion. Okay, so that the derivative of dt of yt, which is dt of the summation k from 1 to infinity y to k minus 1t, this one is, we can exchange them, k from 1 to infinity of d dt y to k minus 1t. Okay, so this is equal to y to k minus 1 prime of t. So we have established that that this yt is differentiable, and its derivative is equal to the sum of them. And because that again, because this converges uniformly, so that the convergence is also, as we know, this is also uniform. Okay, so that we have this one, and y double prime t, it's y prime t, so that this is dt, all right, and summation k from 1 to infinity y prime to k minus 1t is equal to summation k from 1 to infinity d and dt. Okay, so that's and y to k 1 prime t. So this is k from 1 infinity and y double prime to k minus 1 of t. So we know that y prime t is equal to this series sum. So now once we justify that this is series sum converge uniformly, and so the sum is denoted as yt. And because that both of them are they converge uniformly. So y prime of t is equal. So this is equal to the y prime of t, and this series sum is equal to the y double prime of t. Okay, so we have that. So we establish that this is equal and this is equal. Okay, and for all t, okay, so we conclude. So we conclude that yt, all right, is indeed, the steady state solution, okay, of the ODE. Okay, of the ODE. Yeah. So this is the we through this specific example. Okay, we indeed check that our conjecture, the solution is indeed the solutions. Okay. All right. So so I think we have complete the third section. All right. So we will start the fourth section next week. Okay. So I'll stop here.